Okay, let's start.
Hang on, let's sit down first. Right, just spin around your end of the chair. Yeah? Right, you can start now.
Thank you.
Thank you for waiting.
Yeah, I figure out that with the keynotes going really at
They
till
were
the very last
there
minute,
for round.
a couple of minutes late,
Yeah.
and
Sorry.
coffee break. Okay, where are we going? What are we talking about? So when I was at university with our colleagues, between one training course and the other, we were playing a game. Maybe it was just in Italy. It was the game of 36. So you had a square grid, 6 by 6, and you had to put numbers into the grid. And there were rules where to put the next number, where it was horizontally or vertically, diagonal. You had to jump 2 squares or 1 square, and you had to try and fill all the 36 numbers, and it was really tough. So I decided at that point to write a small piece of software that was, solving it for me. And it was, browsing a tree with all the possible options, and it did work. And I wrote it first on a Sinclair Spectrum, and then on an ARM machine. That was one of those that Dana Thompson showed in the pictures, one of the old ones, the RISC PC. And at the time I was excited because I thought that that was artificial intelligence. I thought that that was playing the game for me, so it has a mind by its own. And well, that was not really artificial intelligence, not what we consider as AI today. But it was exciting at the time. So AI, machine learning is pretty huge. What we want to talk about now is actually deep learning. So deep learning is a subset of machine learning, which is a subset of the fascinating overall artificial intelligence. Deep learning is those sets of algorithms that do identify objects, do recognize objects, can be objects in an image, can be objects in a sound, can be the numbers on your plate, and you get automatic tolling, if not an automatic ticket. And it can be recognition in industrial control. So down to, from the big, wide artificial intelligence down to deep learning, that's the focus. It's exciting times because all the recent smartphones, all the recent SoCs in the recent smartphones, they have artificial intelligence accelerators. And actually these are hardware blocks or DSPs that do all the math computation about neural networks. If I oversimplify, it's all about multiplying matrices, multiplying weights by input vectors. There's heavy computational stuff, and these are the accelerators that we are getting in the recent SoCs. The interesting thing is that this is reflecting the ARM ecosystem, a very high pace rate of innovation, and all the neural network accelerators are somewhat different, they have different APIs. Think of the video accelerators, the video decoding accelerators that were introduced a few years ago, and everybody had a different proprietary API. Now it's getting standardized, OpenMax in Android, Video for Linux in Linux, but it took time. So here I see a similar pattern where every NN accelerator has its own proprietary driver and user space source. And the other trend is that the user space part is binary blobs, so it reminds me of the GPU. This is not limited to smartphones only. The developer box, the Synquasa, and this was presented by Yamane-san yesterday, the Ecosystem Day. The Synquasa has a PCIe expansion card with 8 AI accelerator chips. So it's not just smartphones, it's edge devices, it's server, it's also Cortex-M. There's AI ML, that's deep learning inference happening on Cortex-M. And we may expect tiny NN accelerators coming up in Cortex-M microcontrollers. So this is the scope. On the software side, and thank you, Kanta, for helping us with this chart. On the software side, there's a huge amount of frameworks. You have the deep learning frameworks at the top, Caffe, Caffe2, Torch. You have MXNet, TensorFlow, TensorFlow Lite. So some are turning into a modular approach so that you can then use them on your phones. But potentially every framework has a different way of describing the models that need to be deployed on the hardware for the inference phase. Caffe and TensorFlow, for example, have different ways of describing the models that you will deploy. So there are also initiatives about trying to align and have a common set of formats to describe. And then there's the bottom part when you really go and talk to the accelerators. So this is one example, the Kronos initiative about NNEF, and it's about trying to have all frameworks run on all possible runtimes. There's ARMNN, which is a set of math libraries optimized for Cortex-A, and there's CM/SysNN, where the same libraries are optimized for Cortex-M. And they do integrate with the different frameworks. So it's yet another option. And then there's Android-NN, where there's a runtime, there are the APIs for the hardware acceleration, the applications do embed the TensorFlow Lite interpreter or Caffe2. So again, this is just confirming that it's booming, it's here, it's not coming, it's here already. Many different SoCs, many different NN, many different frameworks, many different ways of describing the models. And so I tried to put logos on which initiative is being sponsored by which company and which model is being supported. So this is just basis for discussion. So where do we go from here? And I'm trying to set the stage for the discussion, but I would like to have these as an interactive session as a BoF. So I would like to, there's another microphone here, David. Where do we go from here? Which framework should we look at first? Is there any order of priority? Which model description should we use? Should we target? Should we fork every project and optimize every project for every SoC? Should we look at smartphones only? Should we look at servers? Should we look at microcontrollers? What's the interest in the audience? And who is the first volunteer who would help share their thoughts? The first one is the most difficult. Who is working on AI today? Would you like to help share any thought?
It's my hand.
Thank you, Eric. I really appreciate it. I owe you a drink.
So from our side, we made a couple of presentations in a recent show, like we did Word on MCW, especially around the usage of AI on microcontroller, MCU. So it answers your question from this standpoint. After what framework and so on, we used to be mass market for microcontrollers, this is our strategy, and for the time being we look at it from an agnostic way. So I'm not sure it helps a lot, but at least this is our approach to it.
I saw some of the videos from your demonstrations, and it was pretty fascinating to see Cortex-M recognize objects live from a camera. So, thank you.
I think there's at least three ways that traditional computing and the AI slash machine learning, they work together. One is like the SoC style, that in the SoC you have different subsystems. You have a GPU, you have neural NPU, and then CPU subsystem, right? Then they work together, right? So another way is like on a motherboard, you have CPU, and then there's a PCIe, and then you plug in the GPU card, right, or AI card. Third way is probably you have a GPU itself as a machine, and then CPU as a machine. Then they connect with each other through PCIe. Maybe that's what I inferred from yesterday's presentation. The Socionex, that's the third category, right? So I'm interested to find out how those three are different, and in terms of those three, they serve different purposes for different applications, right? So how to categorize those applications? Which application, the three architecture, which one is the best?
And so the three architectures will be microcontrollers, Cortex-M, smartphones, and servers with PCIe cards.
One is a SoC, has both CPU and the AI subsystem. Another is separated machines. They have inter-machine connecting like PCIe or NIC, right, or network. The third one is on the same motherboard. You have CPU and then you have GPU as a PCIe card.
Yes. And on the software side, any input from your side on which frameworks should we work on all? Is there any priority setting?
I do not directly work. I have not worked on AI or machine learning at all. I'm here to learn.
Okay.
So I come from general purpose server side.
Okay.
So I'm thinking about on a general purpose server, you plug in a PCIe card, which does AI for you. In that case, what's the best way to architect the software stack? And what is this kind of architecture best for? Because there are two other architectures.
Please, Yang, help us, because you have direct experience in all these. Would you like to share?
Yeah, just a couple direct answer to your question. So normally we refer that three type of architecture as being on-die, off-die on-board, and off-board.
Okay.
Right. So that's so what we have shown case in keynote on Monday was quite interesting combination. So first of all, we have on-die with coexistence of NPU, CPU, and GPU, such as Kirin970, based on Kirin970's SoC.
Right.
We also showcase on-die solution with even more interesting combination as in MP-SOC, which is PS block and PL block on the same die from Xenix. Right. You got programmable logic on the edge device, which normally you find FPGA acceleration on the server data center end. And that is also on die. Then you see we have demonstrated off-die on board. Sorry, we haven't demonstrated the off-die on board. We have demonstrated the off-board, which is based on Socionex,
right,
the United States development box, with acceleration through the PCIe slot of a gyro falcon accelerator. Right, so that is off-board acceleration. So all these three different type of architecture, you're right that there is definitely an implication in terms of how software stack is going to be used, be architected on those. So I think what Andrea was trying to say is that there are two different approaches to this. One approach is looking from the high level in terms of framework, in terms of user application. So based on from the user space, from the user application point of view, there should be a consistent view. Right, and how you actually utilize the different architectural acceleration, that's the middle layer, which we're trying to resolve, or we're trying to get a group of people to resolve. So we welcome definitely your input in that. We have some idea, which we might iron out very soon.
You want to help us comment on the different frameworks?
Responding to your question around servers, yes, the servers is there's so much talk at the moment on inferencing. The server market will also need to look at training as well as inferencing, and the GPU architecture is what's currently being used a lot for the training side, while the inferencing side is not. So for that, to answer your question, yes, that is a completely different software stack for the training, and the workload is completely different, and that needs to be considered. The inferencing is very much focused on optimizing what are the target hardware that we're trying to push the machine learning models on. But again, to iterate, the question that Andrea posed to the audience was, should we fork the frameworks and then inference on those for the hardware? No, we certainly shouldn't, because these are the current frameworks we have now. The frameworks will evolve. There'll be new machine learning problems that will be refined, and the models will evolve as per the cyclical model of when we send the inferencing out to the devices, the data we get back will be pushed back to the models, and the models will be retrained, and then the inferencing models will be deployed yet again. So that won't scale in the long term. So we need to ensure that there's a common layer, and this is why there's a lot of effort being done with Onyx and NNEF, where they're trying to find a common exchange format so that this will help developers push the model out to different, so they're not restricted to one framework. They can create an exchange format, a graph that they can then deploy everywhere.
I have a question about So I have a question about where we will make a common layer because this area we will have different hardwares, so that we need each drivers for each hardware in the kernel, and this means that we have some sort of interface for each devices.
Yeah. So there's lots of frameworks for a reason, because one framework will not be the most optimal for your problem space, and that's why there's a catalogue. Now, if we go back to the one more. Yes. One more. Yes. Yeah. So here the colours doesn't help it much, to be honest, but we're seeing a common abstraction layer in two places, which is application support for multiple frameworks.
Is that what's happening with OpenAID? That's kind of an application.
Yes, but so they've done something slightly different in that they've created. I haven't looked at the code base in too much detail, but they've created a fork of the frameworks and optimized it for their real time, and then they've applied the T engine against that. So we all want the same goal, but at the moment the approach there is a bit fragmented, and we're trying to find a way. But definitely we've identified that there's two areas. There's the application support, and then there's the framework support, and then this will enable some of the optimizations to go down, and of course there will be the differentiating layer, which is highly specific on the microarchitecture, and that's where the IP, I guess, will be.
As far as I can see, that the last page, actually that most of the framework supports that ONNX.
Yeah.
So that why don't we focus on the ONNX first and ask Google to support that ONNX in TensorFlow, because that is it seems that another group.
Yeah. No. It's. So your question is to get Google to support ONNX.
Yeah, that's because I was doing this exercise of checking out which framework is using which model description.
Oh, I see. Okay.
Yes. And it turns out that I could see these two camps. One where the Microsoft Cognitive Toolkit, even Apple, Core ML, Caffe, Torch, MXF, they're all being supported by ONNX. So ONNX can read the models from all these frameworks. Thank you. And Yeah, TensorFlow is the only one that currently is not directly supported, but ONNX is providing tools for the conversion. So I should add that as a dotted line. But yes, this is one of the options that we are looking at. So I'm going back to the chart prepared by Kanta. This is one of the options that we are looking at. If we find one common format to describe the models, the pre-trained models from the various different frameworks, then we would not go and change the framework themselves anymore, as long as the frameworks and the common descriptive format do work well together. Then we can focus on the bottom layer, making sure that we have a set of runtimes where we can commoditize the common part. Wherever there are libraries that need to run on the Cortex-A or the Cortex-M, we can make sure that these are a commodity and done once, optimized once for the ARM ecosystem. And we have the expertise with the toolchain team, for example, at Linaro. And then we can enable the right APIs with the abstraction layer for the different accelerators, so that all the players, and I've shown only some SoCs that have NN accelerators. Then all those players can fit in seamlessly, and each one will have their differentiation in terms of performance, power consumption, frame per second. Of course, everyone will have different operators that are supported, so that will imply a different degree of acceleration. So yes, this is one of the ideas we're looking at, and your comment is very well placed. Please.
Yes, Andrea, so can you move to the next page? Oh, maybe next one, last one. Yeah, so for this one, I think for the ONX and NNEF, NN, Android NN, I think they are done on the same level. So for ONX, NNEF, they are the format to describe the model.
Yes.
But for ARM NN and Android NN, they are the API definition to abstract the hardware part, the back end. So they are different things. That's my understanding. So yeah.
For ARM NN, yes, that's correct.
Yeah.
For Android, there are two levels. The NN HAL, I agree with you, yes. And then above, there's the Android NN API, which, if I just go back one slide.
Yeah, so because for TensorFlow, they have a TensorFlow Lite format.
Yes,
That's
exactly.
the model format.
Yes.
Yeah. So
Yes.
in this case,
That's why I've put Android at the same level as the others, because it's the Android NN is using the TensorFlow format.
Yeah, so there are two things we need to solve here. Oh, sorry. Yeah. I think there are two things we need to solve here. One is the model format, right? ONX, NNEF, and TensorFlow Lite.
Yes.
Another thing is to abstract the hardware backend for different operators.
Yeah.
That's my understanding.
Yeah.
Exactly.
Yeah.
Yes. So you're on board.
Thank you.
My name is Daniel. I work in the automotive lab at ARM. What I'd like to see, if you go back a couple
You
of
want to
slides,
have a seat with us. We don't bite.
no, I'm good. Go back a couple slides if you don't mind. To the stack. I don't know if this exists today, but it would be nice to see something like this where you would map like the automotive frameworks that exist now. Right on top of this, to see which ones of these levels in the framework and even in the back end that they actually touch now, to see how prevalent they are. So we could do that for the Baidu, Apollo 2, the AutoWare, and even ROS, for example, if they use some of these.
Would you help us? We would really appreciate.
No. It's a good idea.
It's a very good input,
That
absolutely.
came up a little bit in the automotive discussion as well.
So that's just my comment. I'm not an expert on it. I was here to learn as well. So.
Yeah, no, it's very valuable. Very valuable.
Full of people who are here to
Yes.
figure out what's going on. There's obviously something. But,
Yeah, I agree, and it's not just the automotive market that will slice through all of these. It's all the markets, from financial, health, to all of them that will slice through this.
Yeah,
Go ahead, Rob.
IoT's got use cases.
I was just saying, use the mic.
Clearly it's not, doesn't like microphones.
So I see that there's an Android HAL interface. What exists for non-Android, and what exists that's open that we could actually work on?
It's exactly what we are researching, and yes, it's a very valid point. Today there are tools like TVM and NVM that build the models for the target platform, and usually the target platform is a GPU or a CPU. So those tools built for the GPU with CUDA or OpenCL or any other framework, but not for the hardware accelerators as we are used to in the ARM ecosystem. So that's an area where we should work. The question is, would the Android HAL API be a good one to reuse, or should we look at something lower that would work for the Android HAL and outside Android?
There's also the ARM-INN and ARM compute libraries that are open source.
Well, the Android HAL is a user space API. You have to get to the hardware at some level, so there needs to be an API at some level below that, or perhaps everyone is using VFIO or some user space API just to map to hardware and user space.
Exactly. That reminds me of that's why in the beginning I said that I see the best of the worst of both worlds, the video decoders and the GPU, because you have different APIs, but you also have the user space blob. Because when you see that there's libraries, these libraries embed runtimes for the frameworks, and these libraries run something on the CPU and something is executed on the accelerators. So there's the problem, as you highlight, of the user space blob that comes into the picture. So it's not just defining a video for Linux, a V4L2 kind of API for NN, that's more than that. And even
so is there any hardware that's open, or any driver for hardware that's open?
I think the driver will be GPL. Then there will be a binary blob for the specific, the split between the common libraries and the secret part that.
I'll rephrase it. Is there any stack that is open?
Fully open? I don't think so. I don't think so.
Well,
What's Intel doing in this space?
There are some initiatives. One recently was an NGraph initiative that we're also looking at.
I think, kind of going back to your point, Rob, is I think one of the key questions you're trying to ask is success here for the ARM ecosystem dependent on the entire stack being open? Because the tendency is the closer you get to the hardware, the more likely is going to be closed with some user space component that's also closed.
Well, I don't think that's a question.
Yeah, I mean that's a statement of fact right now. But I think for the benefit of this ecosystem that we're trying to kick off, we probably want a best practice, or at least some reference that's going to be completely open top to bottom. At least that would be what I would advocate. But open discussion, I think.
I think we have some 5 minutes left. Apologies. And then I'll come back to you.
Yeah, I have a few inputs. I think what I'm trying to figure out here is maybe we can ask a question: what Linaro is more competitive or good at doing? Because the kind of machine learning is relatively new, and we are kind of generally speaking, or more low level, close to the machine. We understand ARM well, we understand the kernels, but from my understanding, I think the machine learning is more about high level models, mathematics. There could be lots of changes in terms of the algorithm. For example, there could be some innovation in the next 2 years, and the whole thing has changed. Yeah. A different model is being using. instead of neural network, it could be something else. So what I'm trying to say is, I think we're trying to figure out what exactly the things we can help by leverage what they're good at. For example, we can do something like compiler optimization, because no matter the models change at a high level, which are not quite good at contributing, we could be doing something that is fundamentally useful no matter what the upper level stack is changing.
Yeah, very good point.
Yes, agree. And there's the LLVM, the TVM and LLVM. The target is to target multiple architectures, and there's a lot of work that can be done there for optimization. There's the whole math libraries. A lot of the matrix multiplications is dependent on math libraries, and yes, there needs to be optimizations in there as well. So in the HPC SIG, we're currently targeting.
Maybe it's the battery running out of battery.
We want to target a lot of the math optimizations as well, simply because we want to ensure that we get them highly performant HPC cluster architecture. So the same would apply here, because machine learning is predominantly math.
And another thing, I think by kind of same question probably is asking, he's asking what Intel is doing. I think similar, what is, in terms of ARM ecosystem, what the other ARM vendors are doing. As we see, high silicon have high AI, and I believe there are lots of similar APIs. I think we need to look at what kind of problems or fragmentation, if you like, we have in terms of the AI space, like just we did for the Android space. Every people is implementing something, and I think that's the area we can help here, but it's not quite clear what is the fragmentation is, what's the problem are, and what we can do for it.
Yes. As we summarized just a few minutes ago, we see two areas where we can help. There are two areas where we see we can help by working together. One is trying to identify one format to describe the various models that can work with all. This will have the advantage that the acceleration from the ARM ecosystem would not go and touch the frameworks themselves, because these do evolve. Can't explain that very well. They do evolve over time, and we cannot fork. We cannot ask them to integrate different acceleration. So we need to work below, and the format, finding one common format to describe the various models, that's key. That's the first area. The second area is find the right way of enabling differentiation. Every player in the ecosystem shall have their play at their competitive advantage. That's what characterizes the ARM ecosystem. At the same time, we need to reduce the fragmentation. There's a lot of commonalities in math libraries that are shared. That's a commodity where we can help. So we can help bring all the players together. We can help have a common path to reduce the fragmentation and avoid forking the frameworks. There was a question before we go too far, please.
So there's a discussion says wants everything to be open, but I think what's in the corner and what's in the user space needs to be open. But between the corner and the runtime firmware runs on the accelerators.
Yes.
Right? It can never be open.
Yes.
That's where differentiator is.
Yeah.
But between the runtime OS and the runtime firmware on the running on the accelerator, this interface, right, needs to be well defined, similar like UEFI ACPI, right?
It could be a little higher. Not really here. It could be at this level, because the runtime, there's a runtime here, and that is where there are different operators that are required in the convolutional networks, in the computation part, and not all SoCs provide exactly the same operators. And every SoC over time, with the next generation, or maybe the next firmware upgrade, they will add new operators. So the interface that we need to work on standardizing is not at the hardware level, is within the libraries, so that There are some operators that are accelerated, the others have a fallback in software that is optimized for Cortex-A or Cortex-M. And then when the new release comes, you can enable new operators. But this is where every player in the game can have a different take and can have different operators. So the area is really here. It's not at the hardware level. It's not a video for Linux kind of approach. It's more at the OpenGL layer, if you will.
So you are saying that if I'm an accelerator blender, right? I will develop, of course, the firmware running on the accelerator. I will also develop a small HAL component to plug into the second box from the bottom, right? So and then
have some runtime.
Then everything else I don't touch because it's all right.
That would be the vision. That would be the vision. Yes.
Makes
and
sense.
It may be worked out with dynamic modules, with runtime libraries that provide the different operators and the software fallback.
Right. Makes sense.
Just a quick final point.
Yes, please.
A lot of what we discussed here was the device specific, but if you were to look at it end to end, we've got the training side, but then there's also the deployment and orchestration side. Once the inference models are deployed to the devices, they'll be bringing back a lot of data to refine the models, and the models then need to be optimized yet again and pushed out yet again. So that's a deployment platform that also needs to be considered.
And last but not least, we should set up a CI loop with all those boards that do have accelerators, and we shall identify a common set of benchmarks. I'm not saying that we would publish raw numbers across the boards, because Linaro has a fairness policy and we would never compare numbers from different players. But we do want to set a baseline that would be performance 1 or performance 100%. And then with the CI loop and the right benchmarks in place, whenever we work on any improvement anywhere, we can go and check the percentage of speed up or maybe regression, and then we have done something wrong. So that's another area that we should consider.
So you're saying you're figuring out something like a backend for AI?
It's an area of investigation and see what makes sense to track the baseline. Again, this is just a first chat among friends to identify the next steps.
To go back to Rob's point, you know, where's the top to bottom open set of interfaces for Linux? I don't think the silicon providers will push that. Where they'll push is deployment side, the inference engine for Android. So Google will define all the interfaces in the usual way. And on the training side, they'll operate at kind of fairly high level and it'd be closed source. I think if you wanted a full stack and do both things on Linux, you have to wait a long time as it all falls out, because this is exactly like graphics. And with the added complication that there's a lot of, quotes, innovation, i.e. change, that'll happen pretty rapidly. I mean, it's different from graphics in that there's a feedback loop, as Counter talks about it, where you're constantly changing the training data and feeding back to the model, and you want to put those improvements in the inference side. So it's different from graphics, but it feels like graphics to me.
It's a mix of graphics, GPU, and more. Yeah.
But it is a graphics time, there were no Linaro. Now there's Linaro.
Can you pass the microphone behind?
So in terms of the benchmark you mentioned, there is already the bench by Baidu, and that doesn't have ARM at all in the picture when you go into GitHub and look at it. So maybe a practical goal would be to put ARM into that picture.
Are you volunteering?
Nobody wants to speak now.
Maybe Linaro can change my role. I don't know. I have to find time for this.
Ilias, come.
But I mean, from the developer's point of view, I've worked with TensorFlow, with Keras, with Theano, with Torch. The developer does not want to, well, they do want to care about performance, but at that level, they want to expect that their code will not have to change, because if they have to change everything again, it's a big problem.
Okay. Last one. Okay.
Okay. In my opinion, that I think the blue ones, just like library and the driver, and it's mainly about accelerator. So the chip vendor, I think it's the chip vendor's work. So I think Linaro should not focus too much time on this area. So in my opinion, that the Linaro should focus on the green ones, just like frameworks, and we just talked about. So I spot it's a big market, just like a lot of the company was doing this work. So we should not put all our resource to separate to this market. And just like in my opinion, that the TensorFlow is mainly for the TPU. So in the on area, we mainly focus on the natural network. So I think the TensorFlow is not very good for our solution. So maybe the MXNet and Cafe, maybe we should I don't know, the Linaro could contact with the company about and community. So we should we could community enter the community and work with and try to find some training and influence the site to cooperate with the community together. I think it's a good way for now the resource and the Linaro.
Thank you. Very useful feedback. We have to cut this short. Thanks a lot for all the participation. We have all other meetings starting in 6 minutes. So thank you very much.